Okay, let's return to downtown Decatur. We're going to put our little bit of trigonometry stuff that we just covered in the previous video together with the vector stuff that we did in the video before that one. So here's the coordinate. I've gotten rid of all the details, the street names, and all that jazz. They're gone. All we've got is our beginning point at the courthouse and our ending point at Victory. Remember, you're standing in the street in front of the courthouse. Stranger comes up to you and asks you, where's Victory? And you say you have to go 361 meters. How's that for a sound? Excellent. 361 meters to the southeast. Okay, so that is your displacement vector. Now, I need to say here very clearly, this is going to come up again very soon, vectors are indicated graphically by arrows. Okay? We might call this vector R, you know, with a line over it, and that's fine. But vectors can also be represented graphically, and so here you go. This is the vector R. Okay, actually, let me rotate that a little. That's a little confusing. In fact, it could be confusing. This is the vector R. So that's right. It's 361 meters to the southeast. Okay, but for the person to get there, they have to walk down Ponce and then down Church. So you have to take the components of R. And remember those. We have here Rx, right? Remember, the components are indicated R with a subscript, right? And then you have to go here. This is Ry. Okay? So there you go. Now suppose, well, here we go. Here's the point. We talked about trigonometry last time, and we talked about this particular path that you take walking from the courthouse to Victory in the video before that. But I hope you can look at this and see that there is a triangle here. There's the right angle, right? R is the hypotenuse. Rx and Ry are the two sides. So you can see that when we break a component down into its, break a vector down into its components, we make a triangle. And not only a triangle, we make a right triangle. And remember also that we have imposed this coordinate system, x and y. Okay. Now what if, in order to see how trigonometry connects with vectors, I'm going to ask two questions. All right? And that is this. What if I gave you Rx and Ry and asked for R and theta? Okay. Now, which angle is it that we want? Let's pick this one right here. Let's say that angle there is our theta. We can pick either angle, either this one or this one. But let's just say for the sake of this discussion, I'm asking you for that R and that theta. So if I gave you these two, Rx and Ry, how would we find R and theta? Well, you already know what Rx and Ry are, right? Rx is 200 meters. Ry is minus 300 meters. Right? We already covered that video before last. Well, all we need to do to find theta, to find R is very simple, right? R squared is Rx squared plus Ry squared. That's the Pythagorean theorem applied to this. Now notice when I draw an R without the bar over it, notice I put the bar over it here, which is a little confusing maybe. But there's a bar over it here and not a bar over it there. What's the difference? Well, this value here, r without the bar, is just the magnitude of the vector. Okay. So what if I gave you Rx and Ry, the components, and asked you for the magnitude of the vector, which is r without the bar over it, and theta? Okay. So r squared is just this. That's the Pythagorean theorem applied to, right? R is the hypotenuse, Rx is one side, Ry is the other side. And so we can go ahead and do this. This is equal to Rx squared, which is 200 meters squared, plus minus 300 meters squared. I'm just applying the Pythagorean theorem here to find r. And when you do that, you get 13, let me do this math, 40,000, 90,000, 130,000, is that right? I think that's right. Yes. Equals 130,000 meters squared. R squared is 130,000 meters squared. You can now bring this up here. R squared is 130,000 meters squared. So R is the square root of 130,000 meters squared, which is in fact 361 meters. So R is 361 meters, as advertised at the very beginning when I first brought this example up. Okay? So that's R. To find theta, you just need to apply the angle formula. Theta is the inverse tangent of the opposite over the adjacent. Right? That's how theta is always defined, as the opposite over the adjacent. So theta is the inverse tangent. I'm sorry, that's how tangent is defined, opposite over adjacent. So the inverse tangent is going to be Ry over Rx. The opposite, which is Ry, divided by the adjacent, which is R sub x, that's going to be equal to the inverse tangent of Ry, which is negative 300 over 200. The meters cancel, right? Negative 300 meters over 200 meters, the meters cancel. Put this into your calculator and you'll get theta equals minus 56.3 degrees. Why is it minus? Because it's below the x-axis, right? The x-axis points to the right. Whether it's here or there, it points to the right. The angle is below the x-axis. It's not above it, it's below it, right? It's below it. So that means that it's not pointing into the first quadrant, but pointing down into the fourth quadrant. Okay. So that's what happens if I give you Rx and Ry and ask for R and theta. But what if I give you R and theta? Let's do the other question. What R and theta, that is the magnitude of the displacement, 361 meters, and theta. So R, what if I give you R and theta? And ask for Rx and Ry. Ask for the components of R. Okay, so in the first part I gave you the components of R and you had to find the magnitude of R and its direction. Now I'm giving you the magnitude of the displacement R and the direction, and I want to ask for the components and go in the opposite direction. Well, if you go back to the video from before, the trigonometry video, you'll see that the Rx is equal to the hypotenuse times cosine of theta. That's because of the way cosine is defined as the adjacent over the hypotenuse. Okay. Those were the formulas I circled over to the right hand side of the screen in the last video. So the x component is going to be r cosine theta. That's going to be 361 meters times cosine of negative 56.3 degrees. And when you do that, you will indeed get 200 meters. Okay. And Ry is r sine of theta. Sine is opposite over adjacent. Okay. Here's our angle theta. Opposite, Ry. Right. Cosine is adjacent. That's why we had x there. So here, x corresponds to cosine in this problem because x is the adjacent side to theta. Ry, it applies to sine because sine is the opposite, and the opposite here is Ry. So that's why x and cosine go together here, and y and sine go together here. X goes with cosine because r sub x is the adjacent side. And y goes with sine because Ry is the opposite side, opposite to the angle theta. If we had picked this angle instead, those would be switched. X would be sine and y would be cosine. So this is going to be 361 meters times sine of negative 56.3 degrees, and that does in fact come out to be negative 300 meters. So what we've done here is use, not quite all, but almost all the formulas, trigonometric formulas that we talked about in the last video, and applied it to the example in the first video, the vector problem. And you can see it's because when you add these two components, Rx and Ry, together to get R, okay, when you add those components together, they make a triangle. And so you can apply trigonometry to it because it's a triangle right there. That's really the meat of this particular video, is to make the connection that when you have components of a vector and the vector itself, x component, y component, the vector itself, it's always going to make a right triangle. And so you can use the rules of trigonometry to talk about it. And so we've applied the rules of trigonometry here to this vector problem. Trig plus vectors. Okay. Next up, we're going to add vectors. See you then.